So let's talk about simple harmonic motion in terms of a mass oscillating on a spring. And this happens a lot more in real life than we really realize. For example, even in your car, when they're designing what kind of spring to use for your shocks or for your car seat, they would need to consider the spring, its spring constant, and even information about its harmonic motion. So what is simple harmonic motion? So a lot of times people just say simple harmonic motion, but they write it SHM. And that just means something moving in a repeating pattern that is fairly predictable. So a lot of times we'll have like a ball on a string that oscillates back and forth, so back and forth and back and forth and back and forth and back and forth. And over time it stops because of friction here at the top of where the string is attached and air friction. Same thing with this spring over here. We have a spring on that's attached to a mass, and the mass is pushed back to this position, and this is not necessarily where it ends here, but it's just having you analyze this location. So in reality, this mass would go back and forth and back and forth and back and forth and back and forth over and over and over. Same thing if we had a mass on a spring and we pulled it down like you've done in a lab, you pulled it down, it would go up and down and up and down and up and down and up and down until over time it stopped because of things that we're not going to calculate at the moment. So we have an equation called Hooke's law, which was mentioned before in the lab. And what this says is there's a restoring force, so restoring force, and that's measured in newtons. And a newton is a kilogram meter per second squared. And then we have a spring constant, and a displacement. And the cool thing about Hooke's law is that force is force is force. So we can say also that force equals mass times acceleration. And in this instance, our acceleration is the acceleration due to gravity, which is negative 9.8 meters per second squared. And if force equals force equals force, then we can set ma equal to Hooke's law, negative kx. So for those of you that are interested, you will not need to know this next part for a little while, but if you want to know in the meantime, the derivation then becomes x equals a cosine times the square root of k over m times t. So this is the equation that governs the equations that we use for simple harmonic motion. But like I said, this particular equation, I'm not going to require you to know by heart or be able to manipulate just yet. That's just an FYI. So now let's talk specifically about simple harmonic motion. And what we really need to know is what is the period of the motion. And the period means what is the time taken to repeat the pattern once. So if we had a mass on a spring and it started down here, went up to up here, and then went down again back to the same location that it started, that whole time that it took from going from here to here is the period. So that symbol is T. And so you can think about that as what is the time taken to repeat the pattern once. And that's equal to 2 pi times the square root of m over k. And pi is just the constant 3.14. This m is this mass that's on the spring, same m the whole time. And this k is that spring constant. Same variable that we saw in Hooke's law. The interesting thing about this equation is that it is not dependent at all on how much the mass is displaced originally. So if you only displaced it originally a little bit, and then it went back up, this whole time would be the same if you had the same mass and the same spring constant. And now that you know information about different kinds of energy, so gravitational potential energy, elastic potential energy, and kinetic energy, we can solve for many different variables given one system. So we could solve for the mass on the spring given the period, and then we could use that to find out the kinetic energy at a given location, or the potential energy. We can solve problems that have multiple parts now. The units of the period are seconds, and the units of K are newtons per meter.